Hello, everyone, and welcome. Today, we're diving into a masterclass on 12th Standard Chemistry, Unit 6, Solid State. We're going to go line by line through a crucial section of the TOOT guide without changing a single formula. So if you've ever struggled to visualize how atoms are packed, or if calculation questions trip you up, you are definitely in the right place. We're going to break down every previous year question so it's crystal clear. Let's get started. We're looking specifically at 12th Chemistry Unit 6, Sections 6.63 and 6.64, directly from the legendary TOOT Guide, page number 55 EM. This single page has everything you need to know about cubic structures, completely packed with previous year board questions. We're going to read through it and understand it all, line by line. Here is our roadmap for today's explainer. 1. Introduction and formulas. 2. Comparing cubic arrangements. 3. Solving void percentage questions. 4. Edge length and radius. And finally, 5. Advanced crystallization. We'll start with the core foundational formulas and then build right up to solving those previous year questions. Let's kick things off with Section 1, Introduction and Formulas. We're going to build our foundational understanding of what packing efficiency actually is.
Heading 6.6.3.4, Question 14. Calculate the packing efficiency percentage of a simple cubic arrangement. Appeared in June 24 and 26. Box 1, PY2A. What is meant by packing efficiency or packing fraction? August 2022. Box 2, PY3. Calculate the packing efficiency percentage of a simple cubic arrangement. March 24. Conceptually speaking, packing efficiency is just a measure of how much of the total space inside a unit cell is actually occupied by atoms. Think of it like packing a box for a move. How tightly can you squeeze everything in without wasting space? That's your efficiency.
Packing efficiency or packing fraction from August 22. Total volume of spheres in a unit cell divided by volume of the unit cell, A cubed, multiplied by 100. Then we have the expanded formula from March 24. Number of atoms in a unit cell, N, multiplied by the volume of one atomic sphere, 4/3 pi r cubed. All of that divided by the volume of the unit cell, A cubed, multiplied by 100. This formula is actually super straightforward. On the top, the numerator, we're calculating the total volume of all the atoms present. On the bottom, the denominator, we put the total volume of the unit cell box itself. Divide the two, multiply by 100, and boom, you have your efficiency percentage. Moving on to Section 2, Comparing Cubic Arrangements. Now we're going to put simple cubic, body-centered cubic, and face-centered cubic side by side to really see the differences.
Comparison of cubic arrangements, Part 1. Basic properties. Row 1. Number of atoms in a unit cell, N. For simple cubic arrangement, SC, N equals 1. For body-centered cubic arrangement, BCC, N equals 2. For face-centered cubic arrangement, FCC, N equals 4. Row 2. Volume of one atomic sphere, where R equals radius of sphere. For all three, SC, BCC, and FCC, it is 4/3 pi r cubed. Row 3. Radius of sphere, R, where A equals edge length. For SC, R equals A divided by 2. For BCC, R equals √3 divided by 4 times A. For FCC, R equals √2 times A divided by 4, which simplifies to √2 times √2 times A divided by 2√2, which equals A divided by 2√2. Row 4. Volume of cubic unit cell. For SC, BCC, and FCC, it is A cubed. You definitely need to memorize this relationship between radius and edge length. It is the absolute foundation for every calculation we're about to do.
Comparison of cubic arrangements Part 2, Packing Efficiency Calculation, Step 1. Row 5, Packing Efficiency or Packing Fraction. Substituting values. For simple cubic, 1 multiplied by 4/3 pi times A over 2 cubed, all divided by A cubed times 100. For body-centered cubic, 2 multiplied by 4/3 pi times √3 times A over 4 cubed, all divided by A cubed times 100. For face-centered cubic, 4 multiplied by 4/3 pi times √2 times A over 4 cubed, all divided by A cubed times 100. Simplifying, SC, 1 times 4 pi times A cubed divided by 3 times A cubed times 8 times 100. BCC, 2 times 4 times pi times 3√3 times A cubed divided by 3 times A cubed times 64 times 100. FCC, 4 times 4 times pi times 2 root 2 times a cubed divided by 3 times a cubed times 64 times 100. Mathematically, what's happening here is we're just substituting the radius value in and then canceling out that a cubed volume on both the top and the bottom. It's a very direct algebraic process. Comparison of cubic arrangements, Part 3, packing efficiency calculation, final result. Row 5, packing efficiency results, final formula. For SC equals pi divided by 6 times 100. For BCC equals pi times root 3 divided by 8 times 100. For FCC equals pi times root 2 divided by 6 times 100. Packing fraction percent. SC equals 52%, BCC equals 68%, as seen in September 2020, FCC equals 74%. Just look at how that efficiency increases step by step. Simple cubic is sitting at a pretty loose 52%, but by the time you get to face-centered cubic, it's packed super tightly at 74%. Comparison of cubic arrangements, Part 4, voids. Row 6, voids percent. For simple cubic arrangement, SC equals 48%. Note, low attractive force. For body-centered cubic arrangement, BCC equals 32%. For face-centered cubic arrangement, FCC equals 26%. The logic for voids is super simple, guys. Just take 100% and subtract the packing efficiency we just found. Whatever is left over is your empty space, meaning your void percentage. Section 3, solving void percentage questions. Now let's put what we just learned to the test and tackle some real previous year board questions. Question 12, percentage of void space found in BCC unit cell, March 2020, A, 48%, B, 23%, C, 32%, D, 26%. Correct answer, C, 32%. Explanation. Since the packing efficiency of BCC arrangement is 68%, the void percentage in it equals 100% minus 68% equals 32%. Based on the table we just went over, it's exactly 100 minus 68. Very straightforward question. Packing efficiency of body-centered cubic arrangement. September 2020. A, 52.31%. B, 68%. C, 86%. D, 52.13%. Correct answer, B, 68%. Explanation. According to the properties table, the portion packed by atoms in the total volume of body-centered cubic arrangement, BCC, is 68%. If you've got that properties table memorized, you can knock this question out in 5 seconds flat. Question PY2A, percentage of void space found in FCC unit cell. June 25. 1. A, 74%. 2. B, 23%. 3. C, 32%. 4. D, 26%. Correct answer? D, 26%. Explanation. The packing efficiency of FCC arrangement is 74%, so the void percentage found in it equals 100% minus 74% equals 26%. Once again, it's the exact same subtraction method. Total space minus the occupied space gives us 26% for the empty void space. Question 14. Ratio of volume occupied by atoms in total volume in simple cubic arrangement. A, pi over 4 root 2, B, pi over 6, C, pi over 4, D, pi over 32, E, pi over 3 root 2. Correct answer, B, pi over 6. Explanation. The final formula for the packing fraction of simple cubic arrangement as C is pi over 6. This one comes directly from that algebra substitution step we looked at earlier. It just goes to show why remembering those derived formulas is absolutely crucial. Moving right along to section 4, edge, length, and radius. Let's see how to calculate microscopic distances using edge lengths and atomic radii. Question 10. CSCl has a BCC structure. Its unit cell edge length is 400 pm. The distance between atoms, 1. A, 400 pm, 2. B, 800 pm, 3. C, root 3 times 100 pm, 4. D, root 3 over 2 times 400 pm. Correct answer, D, root 3 over 2 times 400 pm. Explanation. The answer is found using the formula for the distance between atoms in a BCC arrangement. 2r equals root 3 times A divided by 2. To find the distance between atoms here, we just need to pull the correct standard formula for a BCC structure. Question 10. CSCl has a BCC structure. Its unit cell edge length is 400 picoM. Distance between atoms, calculation breakdown. Explanation.
In BCC arrangement, distance to R equals root 3 times A over 2. Here, substituting A equals 400 picoM. Answer is obtained as root 3 over 2 times 400 picoM. You literally just take the edge length A, plug that 400 right into the formula, and solve it. Easy as that. Question 13. If the radius value of an atom is 300 pm and it crystallizes in a face-centered cubic arrangement, the unit cell edge length, A 488.5 pm, B 848.5 pm, C 884.5 pm, D 484.5 pm. Correct answer, B 848.5 pm. Explanation, edge length in FCC arrangement, A equals 4R over root 2, equals 4 times 300 over 1.414 equals 848.5 pm. For this FCC problem, we're basically just rearranging our radius formula so we can solve for A. Plug in 300 picometers, divide by root 2, which is 1.414, and you've got your answer.
Question 16. If the edge length of cubic arrangements SCF, BCC, and FCC is denoted as A, the ratios of the radii of the spheres found in those arrangements are respectively A, 1 by 2A to root 3 by 2A to root 2 by 2A. B, 1A to root 3A to root 2A. C, 1 by 2A to root 3 by 4A to 1 by 2 root 2A. D, 1 by 2A to root 3A to 1 by root 2A. Correct answer, C, 1 by 2A to root 3 by 4A to 1 by 2 root 2A. Explanation. The radii of SCF, BCC, FCC arrangements are respectively R equals A divided by 2, R equals root 3A by 4, R equals A divided by 2 root 2. This is the ultimate cheat sheet. It perfectly summarizes the foundational radii formulas for all three structures. Definitely keep this in your back pocket. Section 5, Advanced Crystallization. We've made it to the final section. Let's elevate things and tackle some of the more complex crystallization problems. Question 18. Aluminum crystallizes in a cubic close-packed arrangement, March 2024. Its metallic radius is 125 pm. Find the edge length of the unit cell. Data panel. For FCC unit cell, radius R equals root 2A over 4. R equals 125 pm. A equals question mark. Solution panel. A equals 4R over root 2. A equals 4 times 125 over 1.414. Answer panel, A equals 353.6 pm. The real key takeaway to notice here is that a cubic close-packed structure, or CCP, uses the exact same mathematical method as FCC. Don't let the different name throw you off. Question 23. Sodium crystallizes in a BCC structure with a unit cell edge length of 4.3 times 10 to the power of -8 centimeters. Find the atomic radius value of the sodium atom. Data panel. For BCC unit cell, radius R equals root 3A over 4. A equals 4.3 times 10 to the power of -8 centimeters. Solution panel. R equals root 3 times 4.3 times 10 to the power of -8, all over 4. R equals 1.732 times 4.3 times 10 to the power of -8, all over 4. Answer panel. R equals 1.862 times 10 to the power of -8 centimeters. By substituting 1.732 for root 3 and carefully stepping through the arithmetic with the scientific notation, the answer falls right into place without much hassle. How do these microscopic packing efficiencies fundamentally alter the macroscopic strength and properties of the metals you interact with every single day? Think about it. How do these tiny, invisible inefficiencies change the physical strength of the steel bridges we drive on, or the copper electrical wires hidden in our walls? It's honestly crazy to think that percentages like 52%, 68%, or 74% are literally shaping the physical world around us. Keep learning, keep questioning, and I'll catch you next time.